Alright, I told myself I was going to do this video before I decided that I didn't want to do it. So yeah, I'm doing it because, well, it's a bit tedious and I see a lot of people, well, I see a lot of just, you know, math people, statisticians, etc. Just writing these things down and saying, oh, we don't want to do the computation because it's annoying, it sucks. It does suck. I'm going to do at least part of it, okay? I want to basically go through what you need to know specifically for exam P regarding the gamma distribution. Okay, so for those of you out there saying there's more to it and there's more general and all this stuff, I know, but I'm not going to go through everything. Okay, I just want to go through specifically again what you need to know for exam P. Okay, so everything's tailored towards that because that's what I'm taking in like 8 days, right? All right. So I have a random variable x. It's distributed with the gamma distribution. I want to first go through the way that I have to remember the PDF. Okay, so let's just go through that. Okay, the PDF, and it is a density function. So sorry I've been messing those up, but this is f of x. The probability density function is continuous random variable. Okay, so is equal to, now the way that I remember this, I found this in, sorry if I'm mispronouncing his name, but Goo's study manual for exam P. Take a look at that, it's free. He has some good things to say, right? This is equal to beta times the PMF of the Poisson distribution. There's a relationship between Poisson and gamma, just like there's a relationship between exponential and gamma. So beta times e to the negative beta x to the alpha minus 1 divided by the gamma function. And it is gamma of alpha. Because remember, gamma of alpha, if alpha is an integer, specifically a natural number, is n minus 1 factorial. So this is not even the way I want to write it though, because for exam P, most likely beta will be some sort of integer, maybe a fraction, and gamma will also be some sort of natural number. I guess I meant natural number, or some sort of fraction. So this is sort of the generalized version. A lot of people don't think of it this way, but this is a nice way to think about it. And again, let me point out, this looks like Poisson, PMF. Okay, let me continue with this. Again, for exam P, and let me just write that. For exam P, typically from what I've seen is that alpha is a natural number. Alpha is equal to some n, which is an element of the natural number, or sorry, well, the integers. Actually, specifically it's going to be a natural number. So let me do boldface n. Okay. What does my formula become now? My formula now for the probability density function for gamma is now f of x is equal to, again, still beta, I don't care about beta, we'll just leave beta there, times e to the negative beta x times beta x to the n minus 1 divided by n minus 1 factorial. And if you, again, look at Goo's manual, study manual for exam P, he goes into a lot of detail about this. He actually computes problems involving gamma distribution using Poisson. And let me just point out again, this looks like, this is Poisson with parameter beta x, right? And n minus 1. So it's like, it's slightly off. But this is how I remember it. Beta times sort of like the Poisson distribution. Poisson mass function. Okay. All right, now that we got that out of the way, again, I'm bringing this up because it's valuable to have a way to remember this. This is how I remember it, because I would have to know Poisson anyway. So this is how I remember it. All right, let's continue. Next thing I want to do is I want to find the expected value of the gamma density, or the gamma distribution. And by the way, how am I getting this? Remember, just recall, this is not super valuable to know, but remember that gamma of n is equal to n minus 1 factorial. That's how I'm getting this. Remember, the gamma function, this gamma function, is a generalization of factorial. All right. Now, let's go through the valuable things you need to know. Okay, so let me get rid of this. And I may have to sort of clean this up a little bit, because I do want to find the expected value. The long and tedious way. If you've thought about this at all, you know that this is a nightmare. But you'll see why. There's another reason why I'm bringing this up. So let me just write it down. Okay, what is the expected value of the gamma random variable? The expected value of x is equal to, by definition, I need to integrate all over the values of the random variable. The values of the random variable go from 0 to infinity of x times the PDF. The PDF, which is, as I mentioned, I remember it as beta times a sort of variation of Poisson. I'm doing it for alpha equals n. It's true for alpha equals any of the random real variable, real number greater than 0, but I'm doing it specifically for n. Okay, so beta times e to the negative beta x to the n minus 1 divided by n minus 1 factorial dx. So immediately you should be saying, oh yeah, this does kind of suck. Why does this kind of suck? Because I'm going to have to do integration by parts a million times, right? Let me clean it up though first. Let's clean it up. So this is now, this is equal to the integral. I'm going to bring the n minus 1 factorial out. I need to combine these x's, and I'm going to leave the betas actually next to this. You'll see why. So this is going to be 1 over n minus 1 factorial, 0 to infinity. Inside here, I definitely have x to the n minus 1 and then x to the 1, so this is going to be x to the n. Okay? What's my power of beta? My power of beta is also beta to the n. And then I have this, e to the negative beta x dx. Kind of a nightmare, but let's see if I can actually fit it on this board. Maybe not, I may have to write some stuff, which I hate doing, but we'll see. If you've been doing these types of integration problems for exam P, which there's a lot of them really, there's a lot of integration by parts problems for exam P that I've noticed. Some books tell you just memorize this formula. I don't like that. I hate memorizing anything if I don't need to. I'm going to do the tabular method. If you don't know the tabular method, you need to know this, okay? If I'm going to do integration by parts, you can use a little trick called liate. Let me just write that down. So integration by parts, that's what we need. You can use liate. So I apologize if I'm going into way too much detail, but this tells you what u is. Okay, I want to write everything up. This tells you what u is. So first thing, you look in the integrand, this piece, what is u? It's either log first, then it's inverse, usually like inverse trig, which we don't care about, or algebraic. Algebraic here, this is my algebraic term, is x to the n. Later on it's exponential, so that's not going to be my u. Okay, so let me get rid of that, because I'm definitely going to need room. Alright, that's how I know what to pick u as, and for your purposes, for exam P, u is almost always the algebraic expression, because we only have exponentials. It's pretty much always with the exponential expression along with algebraic. So I'm going off on a tangent. Alright, u, as I mentioned, this is how you want to do it. U dv. Okay, you know that, I mean, you should know, as many powers as there are, that the degree of this algebraic expression corresponds to how many times I need to do integration by parts. So damn. U is x to the n. dv is this. There's a reason why I kept beta in there, you'll see. So this is beta to the n, e to the negative beta x. We're taking derivatives of u and integrals of dv. So this is going to be n x to the n minus 1. Take the integral here. This is negative beta to the n minus 1 e to the negative beta x. Again, I'm taking integrals here. Okay, continue. This is going to be n n minus 1 x to the n minus 2. And now this is going to be beta to the n minus 2 e to the negative beta x. I want you to observe something. A lot of getting through probability is pattern recognition. Notice the powers of beta and the powers of x. n minus 1, n minus 1, n minus 2, n minus 2. Now to actually write down the integral, the antiderivative of this, what is what we're going to do? We're going to take this, and we're going to go plus. This is just how the tabular method works. Okay, then I'm going to take this piece, damn it, running out of room already. You just go diagonal with each of these. I'm just going to go diagonal. So now the next thing I do is I take this piece and I alternate plus, minus, plus, minus. Minus, okay? And I would keep going. The next one would be down here, it'd be plus. So plus, minus, plus, minus. Now I need to keep going. I need to go all the way down. All the way down. And if you notice the pattern here, what ends up being, what you'll see here is that these are all going to be minus over here. You'll see what I mean. I'm going to go all the way down to n minus 1, all the way down to 2, x to the 1. X to the 1. Notice that n minus 1, n minus 2. 2, 1. This power is 1 less. What's going to be across from here? This has to be beta to the 1. This is going to be beta to the 1 power, e to the negative beta x. Is it going to be negative or positive? Is it going to be negative or positive? I claim, actually, that this one needs to be negative. We may have to fix that. We may have to think about it. Okay? Now keep going on the left-hand side. Take the derivative again. This is now n factorial. Right? This is n times n minus 1 all the way down to 2 times 1. Technically, this is as well. But this is n factorial, x to the 0. What's going to be across from it? Well, now I finally get rid of the beta. Finally get rid of this beta here. So this is going to be e to the negative beta x. Okay? And it looks like I need to do one more on this side. The next derivative here is 0. This one right here is going to be negative e to the negative beta x over beta. So now we need to continue with our tabular method going diagonal. I need to go here. This will have to be negative, and this will have to be positive. And be aware this x is 0, so this is really just 1, right? So if you want, I'm going to just get rid of this. This is just a constant. And if you think about this for a second, we're only going to care about the last term. I'll show you why. It has to do with the bounds of integration here. So this is equal to the following. This is now, I still have 1 over n minus 1. 1 over n minus 1 factorial times, now we use all this. So I start here, I start with the first one. This is x to the n, as a negative, beta to the n minus 1, e to the negative beta x. Keep going. There's a bunch in between here, but I don't have room, right? All the way down to here. All the way down to this piece. And then this is going to, these are all actually minus. Minus and then dot, dot, dot. Minus this one. N factorial e to the negative beta x over beta. Okay? Going from 0 to infinity. So going from 0 to infinity. This illustrates as to why I really don't even care about everything in between. All I care about, because look, I'm going to plug in infinity. When I plug in infinity, I can't really plug in infinity, but I have to do a limit process, right, of some sort, which I'm not going to do. You don't do that in exam P, right? You just sort of make things work. Everything's going to zero out because the exponential dominates these powers of x. When I plug in 0, everything's going to zero out. I mean, look at my integration by parts here. Everything involves x except for the last term. So everything involves x. That will be zeroed out by this except for the last term. That's the only term I'm going to have left. So what is this equal to? Again, I mean, write this out if you want to be more convinced. This is 1 over n minus 1 factorial times, this is me plugging in infinity. When I plug in the upper bound infinity, everything zeroes out. Minus, now I plug in the 0 to everything. I'm using the fundamental term of calculus here. Minus 0, but then I have minus just this term. this is n factorial e to the negative beta times 0 over beta. So what do we have? This negative gets distributed, right? I mean, keep in mind, I have a bunch of terms I'm missing here, but they're all 0 because they all contain x. What is my result? This is now equal to n factorial. This e to the 0 is 1 divided by n minus 1 factorial times beta. This is equal to n over beta. And you should be thinking to yourself, n is alpha. Okay, so this is our result. This is our result, but you should be thinking, I mean, more in general, you should remember that the expected value of a gamma random variable is alpha over beta. Now, I did alpha equals n. Now, I'm not going to do the second moment. It's the same idea. It's just as annoying. Do it. Use a tabular method over here. You can get, well, I can tell you what you should get. Well, let me give myself some more room, but for the second moment, okay, let's erase this. Let's record our thoughts, record my work, because I also want to is equal to alpha over beta, and I have, and I did the computation. By the way, I did the computation for the second moment by myself. I don't want to do it because this is annoying. Okay, I did this. This is bad enough. The second moment, what you should get is, you should get that it's equal to alpha times alpha plus 1 over beta squared. Okay, and you can convince yourself that this is right. And by the way, this doesn't really matter for exam P. I haven't seen this come up whatsoever. I did see the third moment come up at one time. That was annoying. But they gave you the MGF. You should get that the variance, just using your standard definition for variance, which is the second moment minus the first moment squared, you should get that this is equal to alpha over beta squared. These two things are quite important. These two things for exam P, I've used several times. Makes your life a lot easier. Okay, very important. The last, there's two other things I want to do. I want to derive the MGF, which is the most important, I would say. And then I want to talk about the relationship between the sum of n independent exponential random variables and the gamma distribution. Considered proving it? I mean, it's really easy. Maybe I'll just do it. It's really easy. Let's find the MGF though. Okay, what is the moment generating function for gamma? Okay, by definition, okay, I'm looking at the moment generating function of the gamma distribution. This is equal to the expected value of e to the tx. This is the definition. All right. So what is this going to give me? I'm going to write it similar to how I did before. This is equal to, if you recall, what I had was the following: 1 over n minus 1 factorial integral 0 to infinity. Okay, I had these powers of x to, it's actually going to be x to the n minus 1. It's going to be x to the n minus 1. Okay, I have beta in here. Beta is going to be the power n. Now I have this e to the tx, and now I'll use little x because it's now in the integrand. And then I have e to the negative beta x. So this looks good, dx. And there's a reason why I wrote these two next to each other, because I want to combine those, just using properties of exponents, right? No big deal. So this here, this piece right here, factor the x out, so this is equal to e. And what we're going to do actually to make this sort of look the way I want it to, is that this is e to the negative beta minus t x, right? All right, we need to do the damn integration by parts again. So this is equal to, let me just clean it up once more, n minus 1 factorial times the integral 0 to infinity. I'm going to write this the following way: x to the n minus 1, beta to the n, e to the negative beta minus t x dx. Pretty much the same as before. It's almost, if you just go through this, it's almost exactly the same. Tabular method once again. So u, again, u and dv. U is the same, it's almost the same, x to the n minus 1. And dv is this business. Beta to the n, e to the negative beta minus t x. Take some derivatives on the left-hand side. This is n minus 1, x to the n minus 2. This is beta to the n minus 1 e. Sorry, no, this is just still beta to the n. Beta to the n, e to the negative beta minus t to the x, all over a negative beta minus t. So keep going, right? So this one's plus. There's a minus here, but this one's plus using the tabular method. The next one would be minus. And the right-hand side alternates too, because when you integrate, you get a negative, and it changes positive, negative, positive, right? So again, you're going to get, when I write down the antiderivative, it's going to be all negatives. It's going to be negative, 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 negative. I'm going to go all the way down. I'm going to go all the way down once until my powers of x diminish down to 0. And what is this going to end up being here? Well, if you think about it, I'm going to end up getting n minus 1 factorial. N minus 1 all the way down to 2, and then it's going to be x to the 1. X to the 1. Again, think about this. This is n minus 1, this is n minus 2. So once I get to the end, it's going to be 2. This is 1 less. 2, 1 less. All right. On the right-hand side, how do the powers correspond here? These guys, this guy here is going to go, this is to the 1 power. Okay, this is negative 2. Okay, so this is, I'm going to get down to here. And you may have to think about this a little bit. Of course, I'm running out of room, as usual. Okay, so this was n minus 1 down to 2, x to the n minus 2. Sorry, to the 1 power. What's going to be my power of beta minus t? Well, I had to do this how many times? N minus 2 minus 0. So n minus 2 times. N minus 2 times, which means this should be to the, let's see, this should be b beta to the n, e to the negative beta minus t to the x, divided by beta minus t. I'm thinking that this should be to the n minus 2 power. N minus 2 power. This is going to be n minus 1 factorial, x to the 0. This is going to be beta to the n, e to the negative beta minus t to the x, over beta minus t to the n minus 1. Okay, yeah, this looks good. And then this is going to be 0, and then this is going to be beta to the n, e to the negative beta minus t x over beta minus t to the n. Finally, keep track of how you're doing this with the tabular method. This goes here. Okay, I'm going to have some negatives floating around here too. Which one's going to be a negative? Well, it doesn't really matter. This one corresponds here, so this is going to go actually down here. Which one's going to be negative? So it's going to go, this is negative, which means this should be negative, positive, negative. All right. I apologize, it's a little bit messy, but go through this. Go through this. This is what you should be getting. So this is equal to 1 over n minus 1 factorial times I'm going to write all this out, I suppose. Okay, I'm going to write this out. So this is going to be, well, just do it exactly the same. So the first term is going to be this thing. And again, it's going to be this, right? But when I plug in these endpoints, this is going to be 0 again. And when I plug in 0, everything's going to 0 out that involves powers of x. What's the only thing that doesn't involve power of x? Is this one. So I'm going to get 0. These are all the ones that involve powers of x. Okay? This is at infinity. This is at 0. Minus this. This is beta to the n, e to the negative beta minus t to the x, divided by beta minus t to the n. Okay, I already plugged in the endpoints. Everything zeroes out except for that last term, because it doesn't involve the power of x. So this is equal to, oh, and then I had the n minus 1 times that, n minus 1 factorial times that. So this is 0 minus n minus 1 factorial, n minus 1 factorial times this, right? Man, what a mess. This is exactly why people don't want to do it, right? Because it sucks. So n minus 1 factorial cancels here. So this is, and actually when I plug in 0, I'm plugging in an endpoint. When I plug in 0, I get that. And you need to think about something though. There is a condition we need. So n minus 1 cancels, and I get beta to the n, because e to the 0 is 1, over beta minus t to the n, which you can write as beta over beta minus t to the n. So this is my MGF. There's one other thing I want to say though. You have to be careful here. This is not going to converge. This improper integral is not going to converge unless t is less than beta. Now why is that? Because this needs to be a negative power. If I'm taking this to infinity for the upper bound here, that needs to tend to 0. That's only going to happen if t is less than beta. So so it's sort of technical there, but for t less than beta. All right, man, that definitely sucks. Sorry if that was kind of messy. Let's write down an MGF. Okay, so we have everything. We have everything pretty much that we want. Maybe I won't prove the theorem regarding exponential and beta, or maybe I will. It only takes, it's not as messy. It's not as messy, so and it is important. I haven't seen any questions about it, and you actually shouldn't. If you look at exam P syllabus, when they talk about sums of independent random variables, knowing which ones you need to know, they only talk about the fact that you need to know that the sum of independent normal variables is normal, and you also need to know that the sum of independent Poisson random variables are Poisson. Now, in the past, they have put things on the syllabus, or sorry, they have put things on the test that are not on the syllabus. So you may want to watch out for this. It could happen. Let me write down the MGF. And again, this is one of the most important things, because this can make your life a lot simpler. So beta over beta minus t to the n. Do I want to prove this? There's a couple things that annoy me about this. Okay, let me write something down. Okay, so by the way, again, this is extremely important. In fact, I have some questions for you to refer to. Take a look at in the SOA exam questions, take a look at number 165 and 57. Those can be done in 2 seconds if you recognize that you have a beta MGF. Okay? Now, the last thing I want to say is this relationship. So, theorem. And if you're still watching, I salute you. I mean, I know this is really long. It's hard to keep your attention. Suppose that the expected value of xi is equal to 1 over lambda, where xi is distributed expo. So each xi is an exponential random variable. And actually, these are the same. And they all have the same mean. They all have the mean 1 over lambda. This is I equals 1 to n. Okay? The xi's are independent. Independent xi's. You absolutely need that because of the trick I'm going to do. The conclusion, so then t, which is equal to the sum from I equals 1 to n of xi, is distributed gamma with parameters alpha equals n and beta equals lambda. I don't know why the hell they even distinguish between beta and lambda. I hate when people change notations for no apparent reason. Why don't we just use lambda for the gamma distribution? If we're gonna, I mean, different books are different things, but you know what I mean. It's frustrating. What the hell? Can we just agree on something? All these different books use different notation. Whatever. Anyways, let's just show this real quick. It's not hard. Not hard at all. So, proof. MGFs are unique. If I have a moment generating function that looks like this, it's gamma, automatically. There isn't just an MGF that looks like this and just pretends to be gamma as something else. So we're going to use that fact. Okay, so the moment generating function for t of little t is equal to the expected value. Okay, t is the sum of all these. So it's the expected value of t times x1 plus all the way down to xn. Alright? And you should be saying, okay, we're done because of independence, right? Pretty much done. So this is equal to the expected value of e to the t x1, e to the t x2, all the way down to e to the t xn. Now there's one piece I didn't write down before, but that is what is the MGF for exponential distribution? Okay, for exponential distribution, you should know this. I don't want to go through it, but the MGF for exponential distribution is this. It's equal to lambda over lambda minus t. Lambda over lambda minus t. You should say, yes, we're absolutely done. This is lambda over lambda minus t. This is lambda over lambda minus t. They all have the same parameter lambda, so this is exactly lambda over lambda minus t to the n. And we're done. Again, I haven't seen, as far as the SOA goes, I haven't seen any problems regarding this. I'll tell you where I have seen problems, that this is extremely important, extremely valuable, and they could come up. I wouldn't put it past them. Okay, take a look at, if you're studying for the exam, take a look at the TIA website, the Infinite Actuary. They have 4 free practice exams. Go through those. You'll see that there's at least, I think, 1 or 2 that rely on you knowing this. Your life can be so much easier if you realize that the sum of independent exponential distribution, random variables with the same mean is gamma. And by the way, I'll point something else out. As far as the gamma density function, I have seen examples where the PDF ends up being gamma. Okay, they don't tell you that. But if you recognize this, again, if you can point out what alpha and beta are, your life can be a lot easier. Alright, sorry was not my best work, but hopefully you were able to get something out of it. Tell me what you think about it, and request a video if you like. I'm more than happy to cover exponential distribution, what you need to know for exam P. There's a lot, but it's also one of the easier ones, so that's why I haven't done it yet. Let me know what you think. Thank you.